So analytical aspects of SBS data. So in single sequencing, reads were typically derived from sub-clone fragments originating from large insert DNA clone, permitting reading assembly of sequence similarity to recapitulate. So it's just saying that, you know, as I mentioned, when you have a sequence, you need to map back to its source, and the source is actually just a 200 kilobase fragment. So it's not difficult, right? You can align them very quickly. 200,000 is not big. But it says here, in NGS approaches, the output is short. The output is very short, and it's not really suitable for assembly. If you want to find, especially if you have, like here it says, especially it says the particular true when the genome is larger than 1 to 2 million bases. All right, and increase in complexity. That means it's got a lot of repetitive sequence. You know, when you have repetitive sequence and when it's short, it can either be here, it can be there, it can be anywhere. So having short fragments are not very advantageous in this system. So in general, short read data are more readily interpreted by alignment tools. So now if you have a reference genome, then it says having this SBS system is beneficial. Okay. So that means, you know, normally if you read the text and if you read papers, you will find the term genome sequencing, and then you also find the term genome resequencing, right? When you're resequencing, that means, yeah, you've got a sequenced genome, then you want to look for variation. You're resequencing it, and then you're mapping it based on a reference genome, and then you can look for variation. So that's resequencing. But does that mean that when you don't have any reference genome, you cannot sequence? Yes, you still can. And this is called de novo. De novo means de novo assembly. That means assembly, new assembly. All right. And because, here you go, de novo read assembly, alignments. All right. In general, short data are more. So it's just saying that, you know, it's better to use reference genome compared to, or it's easier to use reference genome compared to having to assemble it de novo. But for de novo, you still can be done, but and then requires a lot of algorithms, a lot of mathematics, and a lot of bioinformatics. That's what is required. All right. Now, so it says this is data on analytical aspects. And when you have the sequence, what do you do? So yeah, first you need to align them so you know where the sequence are. And then once you know where the sequence are, even if it's a sequencing or even a resequencing, that means you need to find the differences. All right. So it says, following read alignment, I didn't highlight, to a reference genome, there was an ensuing need to identify variants. So following the realignment, so you need to identify differences, and not only you need to identify differences, you need to interpret. You know, does this mean anything or not? It's probably easy enough if the variation is within the coding sequence, right? Then because the coding sequence you can translate, and then once you can translate, then that means then you can see whether there's a change in amino acid and so on. All right, so you can do that. But most of the cases or problem, well, not problem, the difficulties are when you start studying polymorphisms. What is the difference between mutations and polymorphisms? Well, mutations are ones, it has a negative connotation. What's a connotation? It has a negative feeling about this mutation, but mutation just means a change in DNA. And most times, mutation is associated with a change in function, whereas polymorphism does not constitute a change in function. Right? Normally, polymorphism, like for example, your blood phenotypes, right? So these are called polymorphic groups, right? Because they don't have any significant drawbacks, on viability. Okay, so looking at variation, you don't stop there. You want to see whether it's got any association or not. And it says the most straightforward invariant calling is, of course, detecting single nucleotide variation, also known as substitution on point mutations. This is where you see there's a change in the meaning, but less straightforward was the decision of insertion deletions and blah blah blah. These variants remain quite difficult to detect, and then beyond read length development of, okay, right? So basically you try to find association. Now, other than there's suddenly there's this part of it that says beyond read length, the development of paired end read approaches also has enhanced our ability to detect. So we want to look at variation. If this is what I call, it says paired end. Paired end just means that a particular fragment, you can have sequence from one end and the other. And if you know these ends are paired, that means you know the sequences in the between is a group of sequence. That's all, paired end. Right? So it's just saying that you know head and tail. If you know head and tail, of course you know what's in the middle. Right? So that's what it's trying to say. If you see a paired end, and then let's say one end is called A, the other one is called B, but when you sequence the other genome, you'll find B first, then A, so that you know there's an inversion, this kind of thing. So that's why it says, because otherwise you will not be able to see small variations. But if you have big targeted sequencing, then you'll be able to tell the difference. Okay. Okay, so in NGS, you get data. You need to do alignment, so you try to fix them into a genome, and this will be easier if you have a reference genome. If you don't, you can still do the de novo, which is fine. Once you have the alignment, you need to look for variation. Variation can come in the form of single nucleotide differences. It can also come in terms of huge rearrangement. And finally, it also said, finally in this paragraph, it says that you can also another type of analysis of NGS data uses the structure of counting machines. What was this talking about? Yeah, instead of just looking for variation, you're talking about how many copies have you got of that particular sequence. Remember, you have amplification at the initial step. If it's exponential, if you do copy 10 times, so if you start off with 10, you'll have 100. But if you start off with 100, then you probably have much more. 10 times 100 is 1,000. So in NGS, there's a way to actually look at the effects of amplification. By right, you should have equal amplification throughout the genome. But if you see certain regions are suddenly much more amplified, that means to say that it has a lot to start with. And this has been used for detecting gene expression, levels of gene expression. Okay, and this is RNA-seq. RNA-seq is RNA sequencing. Okay, now this is all by SBS, which is SBS is what? Sequencing-based system. Oh no, sequence by synthesis. No wonder it sounds bad. So the next one is single molecule sequencing. Now this platform, remember I mentioned the ability to detect synthesis at very low levels, and this one you talk about PacBio, and later you talk about nanopore. Okay, so it says massively parallel signal uses SBS approaches use an enzymatic on-surface amplification. You have amplification, it introduces a variety of artifacts. inherent rate of polymerase, error rates of polymerases. I mentioned this before. Fragments were, and especially if you have fragments that's high or low GC, then if it is equal, it's fine. If it's high or low, then it tends to be erroneous. And then there's also misincorporation. Misincorporation are just mistakes. Misincorporate. Error in including. Error in putting in. Misincorporation by polymerase themselves. All right. So with all this, SMS at that point, if you look at this angle, SMS will be advantageous because SMS is single molecule sequencing. It's advantageous because it doesn't require amplification. All right. But because it is SMS, that's why we have now a system that is able to detect single molecules. That means the system must be super sensitive. The problem with super sensitive systems is that it also tends to pick up noise. This is this problem with super sensitivity, all right? So, although the advantages of SMS are obvious, it says the difficulty of overcoming the signal to noise aspects of collecting data from a single molecule is considerable. So the hassle is still a lot, you know, when you talk about trying to clean up data and so on. SMS reads typically have a higher rate compared to SBS. And that's why, compared to SMS, SBS is still the method of choice. You know, although you say that, oh, you're able to do single molecule sequencing, you have long. Well, people, when we talk about NGS, normally will just go by sequencing by synthesis, Illumina. I mean, if you ask me, to us as scientists, well, it depends on the application. Later, we'll see again a small part on application. But basically, what I'm trying to say is that if you ask me, yes, if you ask me, I will stick to Illumina, SBS, right? I don't have any link to Illumina, but Illumina seems to be the most common system people use. Stick on that one. Why? Yes, whatever method that is PacBio or nanopore, I am interested in nanopore. I think is the way forward, but it needs to be developed further. You know, it's not there yet in terms of price, in terms of accuracy, and so on. I'm giving it another maybe 3 or 4 years before, you know, to see whether how it develops into a sequencing system. All right. Under the SMS, there are 2 systems. One is the fluorescent, the other one is the nanopore. Okay, so this is the structure of the paper. So this one talks about fluorescent. You have specifically Pacific Biosciences. This is what I tried to mention earlier: nano fabricated chambers on a silicon surface called zero mode waveguides. You know, whatever that means. But basically, it's just saying that to isolate individual polymerase enzymes coupled to prime DNA template molecules on supplying this polymer mechanism to focus detection apparatus onto the polymerase, effectively permitting the instrument optics to collect data in real time as the polymerase copies the template. It's just saying that now you have a system that allows every time the polymerase makes a synthesis, it can detect that, right? So that's just what it's trying to say. And then because of this, you don't need amplification steps. Measured as sources of error for the sequencing method arise when a correct nucleotide is, so there are issues, you know, it says, because you're talking about enzymes, right? Enzymes are protein, living beings. Well, I would say living, but it's actually an organic being. Sometimes you cannot, it's not a machine as such. So sometimes it goes too quickly, sometimes it goes slow. So sometimes it incorporates too quickly for sufficient time. That means it's just working too fast. If it's too fast, that means even though you have a super sensitive system, it still doesn't detect. So and then of course, and you have too quick, sometimes you have too slow as well. And you have too slow, that means you'll have insertions, right? That means it's too slow, so it detects, and then it detects again before. So this is the issues when you're dealing with proteins, organic compounds. Right? Deletion can also result in corruption of unlabeled. Okay, and then it says over the years, the Pacific Bio platform has increased average read length and accuracy over time by virtue of variety of enzymatic nucleic acid chemistry. So they have improved, right? And current per read error rate is 10%. So that means if you 10% means if you're sequencing 1,000 bases, you're expecting about what? 100 bases mistake. That's quite a lot, isn't it? If you're sequencing 10,000, that means you're talking about 1,000 base mistake. So you don't want that. But these are random errors. Again, this is an important. Keep that in mind because there's another point that talks about random errors. Random errors means the errors can be eliminated with better technology, right? Which means that the consensus error rate improves as coverage depth increases. Coverage. What is coverage? If you have a genome, I mentioned this. If you have a genome, if that particular region you have a one sequence, so you have single coverage. If that particular sequence you have like 10 sequences, that means you have 10 times coverage. And this just so happens that when you sequence this place many times, then this one you have about 5 copies, but this one you have 50. So obviously this one have a higher coverage than that. So coverage means how many times you cover. So normally a good genome sequence project will have 10 times coverage, 10 to 30 times coverage. Then you're confident with the sequence genome. But so it says here that if you have higher coverage, that means the error rate can be reduced. I mean the mistakes don't happen at the same place. It's random, right? You understand what I'm saying? Say for example, the first sequence, right? If you use 100, then you get 10. In 10%, if you sequence 100 bases, you get 10 places wrong. But because this is random, the second time you sequence, it will have another 10 places and 10 places at different places and so on. But along the time, if you sequence 10 times, it will be very unlikely that the same mistake will occur at the same place all 10 times. Right? So that's why that can be eliminated. I'll explain this if you have problems with this. All right. Improves with coverage and depth increases. Maybe I have a question. What does improve as coverage depth increases? I'll give that as a question, and then you'll ask me what it means. Otherwise, you won't ask me. So improvement of the method of instrument have cumulatively allowed for increasing library fragment length. This in turn has placed renewed emphasis. Right. Throughput for instrument run also has been impacted by increasing number of ZMWs for which data can be collected and so on. So now it says it's now possible to have the average read length of excess of 10,000 bases with this instrument compared to. So as I said, Illumina will give you about 250 bases per read. But this one per read, you give 10,000. Of course, this one will be much better, right? Okay. Okay. Then you have the nanopore system. Nanopore, a second approach to SMS commercialized by Oxford Nanopore, uses translocation of single DNA strands through surface position nanopore grid to generate sequencing data by sensing the changes of electrical conductance. Basically, as I said, you have a nanopore protein, then you allow the fragment to run through, then you detect the changes in electrical current. It's quite brilliant. Like Pacific Biosciences, the single molecule nanopore data is subject to signal to noise, again, because it's sensitive, so there's also signal to noise ratio, has a corresponding high error rate when compared to SBS. Then error rate has improved over time. Now, the problem with this is that unlike other platforms, many errors are not random. So there is a tendency for certain sequences to not be sequenced properly. So there's a problem. So that means they can't improve. They can't. So they need to improve. If the sequences are random, that means it's okay. You can just repeat the sequencing, many coverage, and then you'll see. But it says if it's not random, that means it's going to make it become a problem at that particular site. So every time you go into that site, it will be problematic. So that means you can never sequence that site. So then that's why, you know, so it says, oh, okay, so that means error not as readily resolved with increasing coverage. This is what it says. Okay, I hope you're all with me here. So anyway, so finally, well, I think we are getting to the end. Analysis of combined short SBS and long. So at the end of the day, if you want to have an effective genome research, you'd probably be better off doing both. And it's also dependent on what you're doing. If you, for example, if you're trying to find mutations, right? So that means you're looking for variation. So that means you don't care about length. You just want to sequence regions that are very, very you need accuracy, you need high throughput. So obviously you're used by the SBS system. However, if you're actually doing genome sequencing, you know, we know that if you have short fragments, it's not easy to make long contigs. So that means I want long sequences so that I can map it easily. So for genome projects, I would actually prefer the single molecule sequencing. So it depends on the application that you're going to use. You're going to use it for. Okay. The combination of increased read lengths from SMS platforms, improve error rates, and optimize assembly. Now, it's just saying that as a conclusion, towards the conclusion, it says now, because single molecule sequencing has that advantage of being long, if the system currently allows for high throughputness, it doesn't have too much error, it can be assembled, the assembly is improved. Actually, SMS is it will be the method of choice, it says here, you know. Combination, so it says, because it has that improved, SMS is the method of choice for genome assembly. Okay. There is a study in 2005 where they compared long read assembly, SMS, and also by SBS, and then it says this comparison highlighted that the advantage of long read SMS assembly is to provide contiguity, haplotype. What is haplotype resolution? Okay, you know phase? What's phase? Phase means on a single chromosome, you want to know if you have 3 different polymorphisms, right? Let's say in one place you have either A or G. Another place you have either another A or G. The other place is also A or G. You don't know. So those are 3 different polymorphisms, right? Right. So this place it can either be A or G. This one can either be A or G. Now what you want to know is that on this chromosome, let's say you have a heterozygous individual, AG, AG, AG. You want to know whether on one chromosome, is it A, and the other chromosome G, G, G? Or is it A, G, A, then this one will be G, A, G. You understand what I'm talking about? Phase. You want to know the phase of the mutation or the polymorphism. So that's why here it says, if you are able to know, definitely the first is the A, the second is the G, the third is the G is on one chromosome, that is a haplotype. All right. So for that purpose, it says, you know, if you have SMS for contiguity, haplotype resolution, to deconvolute the sequence data in complex areas of human genome that are simply not resolvable, that one I think you use an SMS system. Okay. Here, what it says is that, okay, let's just say the primary reason at this writing, at the moment when this paper was published, for continued human genome sequencing using SBS. Why do people still use SBS, sequencing by synthesis? It's because of cost and throughput, because it's cheaper and because you get more sequence. That's all, right? So that's why I said, you know, if I were to sequence, I would leave it for a few years before I'm going to use the SMS, because right then there will be improvements hopefully by then. All right. The use of HMS continues to be an active research area. Human genomes can reliably assemble into considerably more contiguous genomes as that is possible as SBS. Although recently, even larger genomes such as 18 gigabyte wheat genome has been assembled by combined SBS and SMS. You know. Application of the NGS in biomedical research include DNA-based applications in research, RNA-based applications in research. So that's just so that's this paper. All right. Going back to spectrum. Okay, this paper, if you can see this paper, it says compare NGS. This is a paper that okay. If hopefully you'll be able to understand this now better. Okay, NGS comparison here. So PacBio single molecule, real-time, ion semiconductor, pyro sequencing. Pyro sequencing is detection of, well, this is also by synthesis, but this is detection of pyrophosphate, and this one by ligation. Read length 3 kb on average, 50 to 250, 200. Ion tolerance allows 200 base pair. Error type. Indels are insertions or deletions. For Illumina, the error rate, single pass error rate is 0.1, but for PacBio, the error rate is about 13. Ion tolerance is about 1. Now, at this time, this particular paper, the nanopore is not available yet. Here it says reach per run up to 3.2 gigabases. This one only 35,000. Yeah, although it can single run can run, but in a day, what's the throughput? Right, time per run. Say 1 to 10 days is 130 minutes, and things like that. Cost. See, this is really $2 to American. This is only about 15 cents. Advantages: high sequence yield, low cost, accuracy. This one is you get longest read length and fast, but then it's actually quite expensive. Low yield and high accuracy experiment can be very expensive, right? This one is another comparison. Again, single molecule, ion semiconductor, pyro sequencing is the same thing. This one is the chain termination. This is the traditional Sanger sequencing. Again, accuracy is 99.9. See, all right. I see solid has gives you very, very high accuracy, but Illumina says 98, which is acceptable. This one, again, single molecule has got 87%. Right, so these are from different sources that I've. Okay, this one has got helicose single molecule. See the cost of the machine. Yeah? See the cost of the machine is 999,000. Well, 1 million, right? For the helicos, $1 million. Again, it's got higher rates compared with other reversible terminator chemistries. So at the end of the day, available technology platform, 3 commercially available engine platform, Roche, Illumina, Applied Systems, 3 generation sequencing platform, 3rd generation. So again, see, 2nd generation, this was originally called next generation, but then now you have improved version, so this becomes 2nd generation, this has become 3rd generation. 3rd generation looking at single molecule sequencing, right? Helicos, heliscope. Well, I'm not familiar with helicos and heliscope. Okay, here's got comparison. Now here's got Oxford nanopore, ion torrent. This one, see, average read length is 5.4 kb. All right. So if the error rate is good, then this would have been a very good system. Oxford nanopore. So hopefully what I've done is actually introduce to you the different platforms that is available, and what's more important is at least you know what are the strengths and weaknesses of each. You know, if then you'll be able to argue what would be better for what purpose. Okay,